Hi, my name is Alan Fader, and I am a principal data scientist at Invesco. I am based in New York City. I'm really excited to be here today to talk to you about interpretability and explainability in machine learning. Now, before I get into the details of the methods, I want to take a step back. Think about some of the motivations behind I want to take a step back and think about the motivations here. If you or somebody else is creating some type of model in general, what you're probably doing is trying to create a simplified representation of the world so that you can use it to understand some processes, maybe predict something, utilize it, or even change the world. Now, if you're using a machine learning model, what you did was you took historical past data, and then you used statistics, probability, maybe some linear algebra or calculus to fit and create this model. Machine learning models are really powerful, in part because they can be complex. They can find the complexity in the data. They can find patterns in the data. Maybe they can find which of the causes interact with each other and relate to each other. Maybe they can find on their own nonlinear relationships between the data. And this is really useful because the world is complex. The world has things that interact with each other or are nonlinear. But one of the drawbacks to these machine learning models is that they're not interpretable. Now, lots of people have different definitions of interpretability or explainability. Semantics aside, the way I'm defining it today is we want to understand what is driving a model. What causes this model to give the results it does? Maybe we want to understand what this model is looking at in the data or in the world. Now your model might be put into production, and therefore it might be having effects on lots of people. And sometimes what we want to know is not what drives the model overall, but what drove the individual decision, the individual output from the model, how it affected a person. Now, why do we even care about interpretability? For one, there may be regulatory issues. There may be some type of legal consequences to your models being put into production. The details will likely depend on your jurisdiction and what field you're building your models in, but the government might want to understand what drives the models and what drives a company's decisions on the general population. Even if there are no legal issues involved, you might be working with coworkers who care about the interpretations. They might be used to their own mental models or models that they developed on their own and understanding what caused each and every decision. To get buy-in, you may need to show them the interpretations of the model or interpretations of the outputs. Sometimes in my experience, my coworkers are even more interested in the interpretations of the model than they are in the raw outputs, because it can teach them something about their business that they didn't know about before. Now, if your model is in production and affecting lots of people, you want to ensure that it's not being discriminatory in any way. One of the first steps in ensuring this, but certainly not the last step, is ensuring interpretability in your model. If you don't understand what's driving your model or what drove individual decisions, it's hard to even begin to ensure that your model is being fair to everybody. And lastly, you, as a data scientist or machine learning modeler, may want to understand what drives your models. I've certainly had situations where when I use some of the methods that I describe later, I learn more about my data and the business than I knew before. A number of times I have found data leakage, or I found that I actually misunderstood what some of the variables meant when I started looking into the interpretations. Obviously, sometimes counterintuitive interpretations may be real, but sometimes they may be artifacts of mistakes. Now, you may hear all this and think, well, maybe I shouldn't go for a complex machine learning model. Maybe I should go for something relatively more straightforward, like a simple linear regression. That's interpretable. But as we discussed earlier, if what you're modeling is very complex, there can be real benefits in terms of performance in using a complicated machine learning model. This is why a number of methods have been developed to help fix this logjam. There are a number of methods that help understand the drivers of these black box models. There are a number of methods that show what caused an individual decision in a black box model. And there are a number of methods that take an interpretable model and try to increase its complexity somewhat without losing any interpretability. And these are the methods that I will be talking about today. The first method that I'm going to talk about is called feature importance lists, sometimes also called variable importance lists. In here, as you can see in the graph on the right-hand side of the screen, we can look at all the variables that were in your data set, that were in the model, and see how important they were in your model. The absolute numbers generally don't mean much. What you care more about is the relativity between the top and the lowest, which ones are similar to each other. The way this is calculated is actually very interesting. So take your data set. Your data set has lots of data points and it has probably a number of variables involved. Choose one variable at a time and take that value for all the data points and mix it up. Change them all. At this point, for all your data, one variable is actually totally gibberish. What is there is totally irrelevant to the true value in that data point. Now run your predictions again. Are you a lot less accurate than before? Well, then now it's probably a very important variable in your model. Are you a little bit less accurate than before? That probably wasn't that important a variable in your model. Are you now more accurate than before? Maybe you want to drop this variable and start again. Now, one of the things you notice from the graph on the right-hand side of the page is that all of the lines go in the same direction. This is because a variable importance plot doesn't show you in what way is the variable important. It shows you how important it is, like an absolute value. This leads us to partial dependence plots. Let's look for a moment at the graph on the top right-hand side of the page. These are two models based on a data set from the Titanic, taking all of the passengers on the Titanic, trying to predict whether they died or whether they survived. You can look at the two models and see that specifically we are seeing what is the model's effect of age. For the logistic regression, people were less likely to have survived as they got older. That's actually kind of similar for random forest. But there's a difference. For logistic regression, with one exception, as everybody gets older, they were less likely to survive. A logistic regression predicted that a 70-year-old was less likely to survive than a 60-year-old. The random forest doesn't show that. The random forest basically shows that under 18, people were more likely to survive, but people above 18, there's no really effect. There wasn't really a difference between a 30-year-old and a 50-year-old or anything like that. This is the type of thing you can learn from a partial dependence plot. Calculating the partial dependence plot has some similarities to the variable importance. We take the same data set that we used, and we choose one variable at a time. For example, age. Let's say that every single person in your data set was 0 years old. What would the average survival rate have been? Now let's say that every single person in your data set was 5 years old. What would the average survival rate have been? Now let's look at everybody 10 years old, and so on, up until the maximum age in your data. You can now plot this, and you have your variable importance plot. Now, one of the things about taking averages is you lose any interaction effects. You can go, and if you look at the plot in the bottom right-hand corner of the page, you can see a two-way partial dependence plot. Do the same thing as for the one-way, but then create a heat map, and you can see where the averages are higher and lower. Even though I've shown examples for continuous data, you can actually do the same thing for categorical data as well. Now, as we've said before, another level of interpretability is understanding what drove individual decisions. By looking at feature importance lists or partial dependence plots, you don't know what led to an individual decision. All you know is what drives the model overall. This is where LIME comes in. LIME is actually a pretty cool method. We fit a local model around the data point of interest. So let's say you have somebody going to the doctor and they put in their symptoms and the doctor wants to use a model that predicts their diagnosis. What we're going to do in LIME is you take this data point, this individual that you care about, and you make a bunch of fake data points, artificial data points that are similar to him or her, but different. They might be different in one variable, they might be different in a number of variables. They're not going to be opposite type people, but they're going to be pretty similar. Now, once we've got these data points, take your model and run the predictions on all these data points again. Once you've done that, fit a simple linear regression to these data points, and then the output of the coefficients are the interpretation of what drove the decisions on this individual. For example, you can see on the chart on the right-hand side of the page, this was a model to predict whether a person would be good at soccer or bad at soccer. We have a number of features about their reaction time and certain biological things about how they acted that actually show that this individual would be a good player. We have their age being above 30 years old that predicted that this individual would be a less good player. And the final prediction is a combination of all of them. This is a way in which we can understand what drove our predictions, maybe not only in one direction, but what were the countervailing forces as well. One method that actually gets to some similar results is called SHAP, SHAP values. SHAP values is an interesting method based on game theory. Here, it calculates the contribution of each feature in your data set to an individual result. The way it does it is it starts at a base value, which might be the average of everybody in the entire data set. This is what you might assume if you knew nothing about the person. Now add one variable. Let's say you knew one variable worth of information. How would that have changed this prediction? Add a second variable. How would this have changed its prediction? And so on and so forth, and you can get the prediction change for each and every variable. Now, because your model may be complex, the order that you put these variables in will affect how much they contribute. What goes on under the hood under SHAP is a bit complicated to explain here, but effectively it looks at all situations, all types of orders, and puts them together so that you get the overall contribution of each feature, both in magnitude and direction, for every individual output. One of the cool things about SHAP is that once you run SHAP values on all the data in your data set, you can summarize them and combine them and create things like variable importance lists or partial dependence plots based on your SHAP values. You can then do that even and look at interactions between different variables. As you see in the bottom right-hand corner of the screen, we're comparing age and gender on the final result, and we can see how male or female affects the predictions of age. Now, you may wonder, should I use LIME or SHAP? They actually can lead to pretty different results. And the answer is, it depends on the situation. It depends on what you want to do. One of the big differences between LIME and SHAP is LIME is kind of hyper-local, very, very local. Let's look at an example that I saw from the creator of SHAP in a presentation. He said, let's take an extremely simplistic model, not even a machine learning model. Let's take an extremely simplistic model to predict whether a patient has the flu. In this not realistic and naive example, a patient comes in and says whether they have what their symptoms are. If they have a cough or a fever, but not both, they may be very early in their course of illness for the flu. In that case, the flu medications are likely to work really well, and we're going to give this person a very high priority in getting treated. Let's say they have both a cough and a fever. In this model, we assume, well, they're probably pretty advanced in their course. The treatment isn't going to work as well. It would be great to treat them, but if there are limited supplies, they have a lower priority. And in this model, if they have neither a cough nor a fever, we don't treat them at all. If you were to run LIME on this simple model, LIME would say, let's look at this individual. This individual has a cough and a fever, so they have a mid-level priority. LIME would say that the contribution of cough is negative, and the contribution of fever is negative, because if either of them weren't true, they would have had a higher priority. We looked at them independently. SHAP looks at the population and sees most people around have neither a cough nor a fever and are not going to get treated. Therefore, the contribution of cough and fever are positive, because if they didn't have them, they might not get treated at all. This is part of the difference between LIME and SHAP, and which one is more important depends on your situation. Do you care about the contribution of features to this individual compared to very similar people? You might want to know LIME. Do you want to know about what made this person different than the overall population? You might be more likely to consider SHAP. Now, we've been talking about methods that you can use where maybe you took your favorite black box method, maybe Forest or XGBoost or a neural network, and want to interpret it. Sometimes you don't need to. Obviously, sometimes the world or your data doesn't actually have enough complexity to justify it. When I'm building a model, no matter what it is, I also run something like a logistic or linear regression or maybe a simple decision tree. And if that gives good enough results, great, let's use it. And frankly, if it gives results that are only a little bit worse than my complicated model, I might just use the simple model. But there are things in between. One of my favorite methods, one of the models that I get very excited about, are called GAMs, Generalized Additive Models. If you took some type of intermediate statistics course, you might have learned about GLMs, Generalized Linear Models. Logistic regression is an example, as is Poisson regression, gamma regression, a number of others. GAMs are an extension of GLMs, but one of the big differences is that we use splines to create nonlinear relationships between the X variables and what we're trying to predict. You can see here on the bottom right-hand corner of the screen, we modeled temperature based on year to see what the overall global temperature is based on the year. The data itself led to this shape. This shape isn't some type of pre-built shape you could get out of a GLM or any type of pre-built tool. This found out its own when it was relatively flat, when it increased by a lot. Now, you might be worried that the splines would lead to overfitting, but the GAMs have a penalty on wiggliness, to use the technical term here. There are some drawbacks to GAMs relative to, say, a random forest, in that the GAMs don't find interactions on their own. You'll have to add that in. But it has a number of benefits as well. For one, it actually comes out with standard errors. So you can look at the standard error of your data, of any data point, and the data point at every, say, year in this situation. And of course, when you plot something, you are plotting the actual effect of the model. You're not estimating, you're not getting the average effect, you're not basically understanding what's going on. Here, you can look at the plot and actually understand what drives the model. So, in conclusion, there can be, and usually often is, a real trade-off between interpretability and complexity and possibly accuracy. But don't just leave it at that. I've had times where I've worked with data scientists who maybe build a great gradient boosting model, hand it over to an internal client. The internal client's first question is, well, what caused this decision? What does this model do? And then sometimes the data scientist says, I don't know. If you really want to understand what's going on, I'm going to instead build you a less performative model. Don't do that. If you think that the complexity of your model is really important and adds a lot, then interpret it, look into it, and work hard to get the buy-in. The other thing that I find really exciting about this is that this is a developing field. Some of the methods that I've shown today have changed in the past few years. This is actually changing all the time. There are new methods all the time within model interpretability that can help you. If you're interested about this, maybe do some searching on your own. Maybe in a few months, there'll be a new model that blows all these methods out of the water. So if you're interested in learning more, you can look at the slides. I have an appendix in the back where I include links to online books and other useful articles that will tell you more about many of these methods, and actually many methods that I didn't have time to talk about today. They will also refer to packages in Python and R that you can use on top of your already existing models. Thank you very much and enjoy the rest of the conference.